looking at f of xy equal x squared y, where x of t equals cosine t, y of t is a natural log of 1 plus t over pi. At the point where t equals pi, we find the values of x, which would be -1, and the value of y, which would be easily found to be natural log of 2, which is about 0.693. This gives us a point in three-dimensional space in the xy plane. X equals -1, y equals natural log of 2. Now, if we look at the x function and the y function, this is our x function, which is a cosine of t. Here's our y function, which is a natural log of 1 plus t over pi. I didn't shift that exactly correctly. But in any case, it gives you a schematic. When t equals pi, and of course that would correspond to a point here or a point here on the graph. So this would be the value of y, which would be, of course, natural log of 2. And the value of x would be the value you get when you project this over to the x-axis. The rate of change of y with respect to x is, of course, the derivative y prime. And the derivative of y is easily found to be just 1 over the quantity pi t. I'm not sure I even wrote that down here somewhere. In any case, the derivative, it's not 1 over pi t. It's, where's my function? Derivative of my function here is going to be what? Inner function gives you 1 over pi. Then you have the reciprocal of 1 plus t over pi. So what you get is 1 over then pi plus t. I think I said it wrong a minute ago. And you evaluate that. Pi plus t will be pi plus pi when t equals pi. So 1 over 2 pi, reciprocal of 2 pi, 2 pi being a little over 6, turns out to be very close to 0.16, and actually just a little less. I was thinking it might, I was kind of estimating it'd be a little bit more than 0.16, but I kind of missed that estimate. Okay, anyhow, you have this value for y prime, and of course x prime would be the negative of the sine of t. And the value of x prime would be 0, which actually leads to a little difficulty in what I was trying to convey here. I thought through a lot of things when I made up the problem, and I just kind of had a bonehead oversight when I chose pi. So we'll see what that does. Okay, in any case, again, you have the point -1 natural log of 2, and we have the derivative of y, which is this, and I actually find the change in x, the actual change in x, due to a change in t of 0.02. Now, if you looked at the preceding videos, you saw where we did this for the better choice of a point where where t was pi over 4. Okay, so again, referring back to that example, and by comparison, the delta x here that we estimate based on the derivative, since the derivative is 0, would actually be 0, and you would have no dimension here. So I took the liberty to find the delta x, which would actually be 0.0002 approximately, just by taking the difference between x at pi and x at pi plus 0.02. Now it's implicit that we're looking at a delta t of 0.02, implicit in terms of the example we did before. The same change in t this time. Okay, so now the question is, we've got all this information. If t changes by 0.02, by how much does x change? Well, it turns out it changes by about this. Although if you use the delta x approximately equal to dx dt times delta t, since dx dt is 0, you would actually get 0 here, and all your change would be due just to the change in the value of y. Okay, the change in y estimated based on the value of the derivative is going to be 0.02 times your 0.159154. Okay, so I ballpark that as 0.003. It'd be much closer to 0.0032. I didn't go to that level of detail. You can in your own calculations to verify, but I didn't want to have too many significant figures to write down here. So, looking at where we are. When t equals pi, again, we're at this point just by evaluating x and y. And if t changes by 0.02, we find that y changes by approximately 0.003. And I should probably make that an approximately equal sign, shouldn't I? Approximately 0.003, even better, 0.0032. In any case, we have a change in y due to this change. We have a change in x due to the change 0.02. Now I'm using the actual change in x here, at least rounded to one significant figure, rather than the change that would be predicted based on the derivative, which would be 0 for the reasons I have already explained. So we have this picture. Now, the value of the function at this point is what? Well, we can evaluate x squared y. The value of x is -1. The value of y is about 0.693. So the value of the function is going to be x squared y, -1 squared times 0.693, or -1 squared times the natural log of 2 if you want it more accurate. And those are going to be the coordinates of the point we have up here on the graph of the function. Okay, now using the change that we predict in y, a change of approximately 0.003, how much is the value of the function going to change? The value of the function being the z coordinate, z equals f of x, y equals x squared y. Well, the change in z is going to be approximately equal to the partial derivative of f with respect to y evaluated at this point, because what does the partial derivative with respect to y give you? It gives you the rate of change of z with respect to y at this point. Now, if that rate of change continues, then we can multiply that rate of change by the change in y and get the resulting change in z. In this case, we're going to multiply x squared, well, the partial derivative with respect to y is just x squared. Okay, treating y as a constant. The derivative of this is clearly just x squared. So here's your partial derivative with respect to y. That's the rate at which this thing climbs, in this case, with respect to motion in the y direction. That will therefore be the slope of this line in this plane through -1 natural log 2, 0, parallel to the yz plane. Okay, so that's kind of the slope of this line, which we can multiply by the run here, which is 0.003, to get the rise, which is your delta z hat. Now I put a hat on this delta z because I've got another delta z over here, and I call this delta z tilde. Well, that product, x squared, well, what's x? X is -1, so x squared is 1. And then multiply that by delta y. And of course, x squared is 1. Remember, that's your partial derivative with respect to y. That's the actual slope of this line in this plane parallel to the yz plane. So we multiply the slope by the change in y, Now, that can be a little confusing because you're used to seeing y versus x, so the change in y would be the rise. Here, the change in y is the run from here to here. We multiply that by the slope, we get the rise. So the rise, since the slope is 1, the rise is equal to the run being 0.003. So we get delta z equals 0.003 if we just look at the change in the y direction. Now in the x direction, and let me caution again, in fact if we use the same idea here, the partial of f with respect to x is actually 0. Okay, so I'm kind of fudging when I say the partial of f with respect to x is equal to, well, first of all, it's equal to 2xy, 2 times the value of x times the value of y, times delta x. Now that's all right. That really doesn't equal negative 0.0028 because the change in x is really 0 if we use the actual derivative of x with respect to t here. But fudging a little bit, letting delta x equal 0.0002, we find that the change in z due to the rate at which the function changes with respect to x, in other words, change in this direction, is negative 0.0028. So, we add these two changes together to get the net change in the value of the function. 0.0028 is much smaller than 0.003. We end up with a change of approximately 0.00, it'll actually be about 0.0029 if we do this all to the appropriate accuracy. Now we want to look at uncertainties in these calculations and how they might affect our estimate and how they might affect our confidence in this approximation.